So let's start. First of all, let's understand what amortized analysis is. Amortized analysis is the analysis technique used for algorithms where an occasional operation is very slow but most of the other operations are faster. In amortized analysis, we analyze the sequence of operations and guarantee the worst case average time, which is lower than the worst case time of a particular expensive orientation. So here, I would like to explain it using an example. And the example that we have chosen is dynamic array. So first understand what a dynamic array is. Unlike the static array, dynamic array does not have a fixed size. The size of this array depends upon the number of inputs. As you can see from the figure, initially the size is only 1, and when another element has to be inserted causing overflow, it doubles the size. So every time what happens is once the array gets full, it doubles itself in size and makes space for the upcoming elements. So it does not happen that simply because we do not know that the memory after the currently existing array is being occupied by something else or not. So what we do is allocate a larger memory and then copy the currently existing array elements in the currently existing array to the new array. So here, as you can see, from 1 to 2, once it gets full, it doubles itself and then and makes space for 3 and 4. After that, it becomes of the size 8 and then makes for 5, 6, 7 and so on. So let's understand how amortized analysis works. So for amortized analysis, there are 3 methods that we are going to consider: the aggregate method, accounting method and the potential method. So let's start with the aggregate method. So aggregate method is the simplest way of amortized analysis. All we have to do in this method is take the average. So here first we calculate the big O of the total cost and divide it by the number of operations. So the big O of total cost here can be determined by big O of the sum of the cheap costs and the sum of the expensive operations. So here from the table we can see that there are first let's understand what the cheap and expensive operations are. The cheap operations are the ones which have a very low cost. That is, for example, inserting an element where already a space is allocated. So that will need the cost of only one. For example, when we have to insert 6 or when we have to insert 12 and many others. While the expensive operation is when we have to double the size of the array. That is, while inserting 2, 4, 8 and so on. So here this table shows the cost and the item number while inserting for each of them. So let's now calculate the cost of both the cheap and expensive part. Here the cheap items are the cost will be nearly n because each cheap insertion will take only one cost, and for n there will be around n cheap insertions, and we can consider the cost to be n. While calculating the expensive items, we can observe that here every expensive operation occurs in the power of 2. So for example, here first one, second, fourth, that is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 4 and 5 and similarly. So while adding this up, the sum turns out to be double, almost double the size of the number of elements inserted. So here the total cost, the total cost for expensive operations will be 2 into n, and the total overall cost will be O of n, that is for the cheap ones, and 2n for the expensive ones, and turn out to be O of 3n, that can be represented as O of n. Now we have to divide it by the number of operations, that is n. So for amortized analysis, O of total cost is given here and divided by total number of operations, that is n. So O of n by n, so we get O of 1. So this is measurement using the aggregate method of amortized analysis. Now we will go on to the accounting method that we discussed. Accounting method. Here the approach is to provide a fixed charge for each iteration and use some of the charge for cheap operations and save the rest of the charge in the bank for larger operations. The challenge here is to maintain a balance of 0 or greater than 0 in the bank at all times. In dynamic array, the fixed charge given to each iteration is 3. As you can see from the figure, when the first element is inserted, it has a charge of 3, out of which 1 is used for insertion of the element in the array, and 2 is still the balance. Out of this 2, 1 will be used to copy the first element to the larger array, because this array is full now. And so now from 2 the charge has become 1, and when the second element is inserted, it will have 2 charge remaining after insertion. So when this array of 2 gets full, and it has to be transferred to it has to be copied to an array of 4, this 2 will be the charge of the 2 saved will be used, 1 to copy the second element and 1 to copy the first element, and hence the second element will have now charge of 0. The third and fourth element will have the charge of 2 after insertion, which will be used, 1 for copying themselves when the array is to be doubled, and 1 to copy the previously existing elements. So this pattern will be followed for larger arrays from 4 to 8, 8 to 16, 16 to 32, and so on. Since each operation has a constant time of 3, under the bigger notation, amortized time will be O of 3, which can be written as O of 1. So this was all about the accounting method. Now we'll take a look at the third method, that is the potential method. So in the potential method, the concept is similar to the accounting method. Here the potential is analogous to the bank in the accounting method. The main difference is that to determine the current balance in a bank in the accounting method, what we had to do is to start from the beginning and calculate step by step how much balance is there in each iteration, and then we can get to the ith iteration or any iteration that we want, but which is not the case in the potential method. In the potential method, we can independently derive the potential at any point of any state using the function phi of h, where h is the particular state. Now let's discuss about the function. For the dynamic array, the phi of h is 2h minus the size of the array at that position. The amortized time of the ith operation, or h of I, is given by c of I plus phi of h of I minus phi of h of I minus 1. Here c of I is the cost, phi of hi is the phi of the that iteration, and phi of hi minus 1 is the phi of the iteration before that. So here, since h of I consists of the parameter size, and the size of the array will not be the same every time, so there will be two cases possible. First will be the normal case, where the size of the array does not increase, and second will be the expansion case, where the size of the array will be increasing. So let us calculate for both of them. So now let us consider for the normal case. Here, while we apply c of I plus phi of h of I minus phi of h of I minus 1, the c of I here will be 1, because the memory for insertion is already available. Here all we need to do is to replace phi of h of I with the equation given below, 2h minus the size. So here instead of h we have I. So the equation after expansion will be 1 plus 2i minus the size minus 2i plus 2 plus the size. So here 2i terms get cancelled, and the size minus size and plus size will be cancelled, because the size before and after the insertion will be the same. So all we are left with 1 and 2, that is the total will be 3. Now it will be a bit different for the expansion case. In the expansion case, when we apply the equation c of I plus phi of hi minus phi of hi minus 1, c of I here will be I plus 1, because first we need to copy the I elements in the previously existing array, and then add one more element to the array. So the cost will be I plus 1, and 2 of I minus size 1 minus 2 into I minus 1 in minus size 2. So here size 1 and size 2 will not be the same, because before expansion and after expansion the size of the array is doubled. So the size 1 in this case is the size after the expansion, that is 2 into I, and the size after the expansion, size before the expansion will be I. So replacing size 1 with 2i and size 2 with I, we get the following equation: I plus 1, 2i minus 2i minus 2 into I minus 1 minus I. So now separating the coefficients of I and the constants, together we get 1 plus 2 minus 2 plus 1 into I plus 1 plus 2. This whole term gets cancelled out, and all we are left with is just 1 plus 2, that is 3. So here in the both method we get O of 3, which can be reduced to O of 1. So this was all about the potential method. So now let's summarize the discussion. We started with the definition of amortized analysis and understood when it can be used. Then, with the help of the example of dynamic array, we got to know about the three methods of amortized analysis. First is the aggregate method, which is the simplest approach. Here, all we had to do is to calculate the average to get our time complexity. Next, we saw the accounting method and the potential method, both of which are conceptually similar. Here, we assign a charge to each iteration and use some of it for short and saved the rest for the larger operation. The main difference between the two is that the potential method we were able to determine the balance, that is the potential, at any point using the potential equation. In all methods, we found the time complexity to come out to be O of 1. Here, we discussed this method using a fairly simple example, but this analysis can be applied to complicated algorithms as well. So I would like to conclude this video by saying that amortized analysis is one of the most useful and accurate methods of analysis. Thank you.